You use a ratio of polynomial functions to form a rational function, like y equals the polynomial or binomial x plus 3 over the binomial x plus 16. A rational function is a function that you can write in the form f of x equals p of x over q of x, where p of x and q of x are polynomial functions. The domain of f of x is all real numbers except those values for which q of x, the denominator, equals 0. The graph of a rational function can be continuous or discontinuous. The graphs of 3 rational functions are shown below. First, a continuous graph, and then 2 discontinuous graphs. Take note of the differences. First, a continuous graph. A graph is continuous if it has no jumps, breaks, or holes. You can draw a continuous graph and your pencil never leaves the paper. There is no value of x that makes the denominator 0. Taking note of the function itself, in this case y equals x squared over x squared plus 1, note there is no value of x that makes the denominator, x squared plus 1, 0. And our discontinuous graph examples. A graph is discontinuous if it has a jump, break, or hole. Considering the graph of this function, the graph has a hole at x equals -2. The function is not defined here. Considering the function itself, y equals, in the numerator, the product of 2 binomials, x plus 3 and x plus 2, over the denominator, x plus 2. Note, if x equals -2, the denominator will be 0, so x cannot be -2, and our function is not defined at that value, x equals -2, corresponding to the hole we see in the graph. And our second discontinuous graph example, in this case the graph jumps. If you were drawing this graph with pencil and paper, you'd have to lift the pencil in order to draw the 2 parts of the graph. Considering the function, y equals x plus 4 over x minus 2. If x equals 2, the denominator will be 0, so x cannot be 2. And notice graphically, our graph is not defined at x equals 2. Take note, key concept, point of discontinuity. If a is a real number for which the denominator of a rational function f of x is 0, then a is not in the domain of f of x. The graph of f of x is not continuous at x equals a, and the function has a point of discontinuity at x equals a. A point of discontinuity can be removable or non-removable. First, a removable discontinuity is a point of discontinuity a of a function f that you can remove by redefining f at x equals a. Doing so fills in a hole in the graph of f with the point a, f of a. Next, a non-removable discontinuity is a point of discontinuity a of a function f that is not removable. It represents a break in the graph of f where you cannot redefine f to make the graph continuous. The graph of y equals the product of 2 binomials, x plus 3 and x plus 2, over x plus 2, shown at the right, has a removable discontinuity at x equals -2. You can make the function continuous by redefining it, essentially filling in that hole with a single point. If we redefine y as a piecewise function, so that it behaves a specific way on some parts of its domain and a different specific way on other parts of its domain, we can fill in the hole and make the function continuous. So, if we let y equal x plus 3 times x plus 2 over x plus 2, the original expression from the function, if x does not equal -2, note -2 is the value that's not defined for this function, and let y equal 1 if x does equal -2, this piecewise function has no gaps. The hole is filled by the point created by the lower part of this piecewise function. The graph of y equals x plus 4 over x minus 2 has a non-removable discontinuity at x equals 2. Note the graph. We have a vertical asymptote at x equals 2. There is no way to redefine the function, as we did in the previous slide, at the point 2, or x equals 2, to make the function continuous. When you are looking for discontinuities, it is helpful to factor the numerator and denominator as a first step. The factors of the denominator will reveal the points of discontinuity. The discontinuity caused by x minus a to the nth power in the denominator is removable if the numerator also has x minus a to the nth power as a factor. Problem 1. Finding points of discontinuity. What are the domain and points of discontinuity for each rational function? Are the points of discontinuity removable or non-removable? What are the x and y intercepts? Part A. Y equals x plus 3 over x squared minus 4x plus 3. Well, in order to identify our points of discontinuity, and therefore domain, we'll need to have each of these polynomials in their completely factored form. So we'll factor the numerator and denominator to check for common factors. The numerator is already factored. It will stay x plus 3, but the denominator, x squared minus 4x plus 3, can be factored as x minus 3 times x minus 1. Considering the denominator, we can state the function is undefined, where x minus 3 equals 0, causing a 0 denominator, and where x minus 1 equals 0, causing a 0 denominator. That would be at x equals 3 and at x equals 1. The domain of the function is the set of all real numbers, except x equals 1 and x equals 3. There are non-removable points of discontinuity at x equals 1 and x equals 3. The x-intercept occurs where the numerator equals 0. Recall the numerator is x plus 3, so a value of negative 3 4x causes the numerator to equal 0 and identifies our x-intercept. To find the y-intercept, let x equal 0, substitute 0 4x in the equation, and simplify. So y equals 0 plus 3 over 0 minus 3 times 0 minus 1. That simplifies to 3 over negative 3 times negative 1, which is 3 over 3, and that's 1. Part B. How about y equals the binomial x minus 5 over the binomial x squared plus 1? You cannot factor the numerator or the denominator. Also, there are no values of x that make the denominator 0. The domain of the function is all real numbers, and there are no discontinuities. The x-intercept occurs where the numerator equals 0, so where x minus 5 equals 0, that's at x equals 5. To find the y-intercept, once again, let x equal 0 and simplify. Substituting 0 4x in the original equation, it becomes y equals 0 minus 5 over 0 squared plus 1, and that works out to be negative 5. Part C. How about the function y equals x squared minus 3x minus 4 over x minus 4? First, factor the numerator and denominator completely. X squared minus 3x minus 4, our original numerator, can be rewritten as the product of two binomials, x minus 4 and x plus 1. The denominator is already factored, that's x minus 4. Note we have a common factor in the numerator and denominator, this x minus 4 binomial. The function is undefined where the denominator, x minus 4 equals 0, so that's at x equals 4. The domain of the function is the set of all real numbers except x equals 4. Reconsidering the factored form of our equation, y equals x minus 4 times x plus 1 over x minus 4, we can note that except at x equals 4, we could essentially cancel the x minus 4 in the numerator and the x minus 4 in the denominator, and y is simply x plus 1. Because y equals x plus 1, except at x equals 4, there is a removable discontinuity at x equals 4. Note the graph. The graph represents the equation y equals x plus 1, except there's a hole where x equals 4. At x equals 4, y equals x plus 1 equals 4 plus 1, and that equals 5. So you can redefine the function as a piecewise defined function to remove the discontinuity. Here's how that would look. Y equals x squared minus 3x minus 4 over x minus 4, the original function, if x does not equal 4, and y equals 5, filling in the hole, if x does equal 4. The x-intercept occurs where the numerator equals 0. That's at x equals negative 1. And be careful, you may be tempted to think that at x equals 4, the numerator also equals 0, because x minus 4 is 0 when x is 4, but remember, x equals 4 is not defined in our function, it is not part of our domain, so it should not be considered as a possible value for the x-intercept. To find the y-intercept, let x equals 0 and simplify. Our function becomes y equals 0 squared minus 3 times 0 minus 4 over 0 minus 4. Simplifying, that works out to 1. Your turn. What are the domain and points of discontinuity of the rational function? Are the points of discontinuity removable or non-removable? What are the x and y-intercepts of the rational function? First, part A. Y equals 1 over x squared minus 16. Note the denominator is a difference of squares. Part B. What about y equals x squared minus 1 over x squared plus 3? And part C, y equals x plus 1 over x squared plus 3x plus 2.